So what's really new today is that we are going to establish for ourselves the general mole balance that applies to any reactor. So let's imagine some kind of arbitrary reactor. It doesn't have a regular shape necessarily. So let's say this is our reaction space. And let's say we are fed by a stream here. So that's our inlet stream of our species, of our reactants. And then let's draw an exit stream here. And now we would like to write a mole balance over this whole space. And to do that, we can define the number of moles in the space, first of all. So let's write it on some arbitrary component I. So we can say that we want to determine the number of moles of component I as a function of time. So to do that, we proceed in the usual way. We think about how does the number of moles of component I change in this space. So we can write here rate of change, so dBT of the moles of I. So the rate of change of I, we can see the number of moles of I will change in the space when we feed I into the reactor and when component I leaves the reactor. So we'll say here Fi in, and then we lose I in the exit stream, Fi out. Right, so that's one side of it. Now, component I, besides just entering and leaving, we assume there's also reaction happening. So component I could be reacting and disappearing in a reaction as well. Now, we've defined Ri to be the rate of formation of component I. So let's say component I is forming. So let's talk about it as if it's forming. So component I is forming. And of course, it's forming across this whole space. And we can imagine that the concentration of I is changing across this space, right? So as our stream enters the reactor and it passes through whatever internals are there and it continues on its journey, its concentration is changing due to the reaction. And as that happens, our reaction rate is then also going to change. Because remember, our reaction rate is generally a function of both the concentration and the temperature. And it's a function generally of all the species in the reactor. So we need to say that, yeah. So C as a vector of all the species, all the concentrations. So it's a function of all the concentrations and the temperature. So as we pick different points in this reactor, we are getting different reaction rates. So we can't point to this whole reactor and say, well, there's the reaction rate. I'm just going to take this reaction rate at this specific point, and I'm going to multiply by the total volume. So the total volume of this reactor, let's call that V, and let's call this the reaction rate at some specific point X, Y, Z. Right, so if we pick some arbitrary X, Y, Z, we'll get some reaction rate there. But we don't know whether that's representative of the whole reactor. This whole space, we might have a high rate here. We can imagine we have a high rate here because we have a high concentration of reactant near the inlet point. But as things react and as it passes through this weird geometry, by the time it reaches the exit, we can imagine the reaction rate here is much lower. So we don't know how concentration and temperature has distributed itself across the space. And what we are trying to do currently is develop a nice general equation that will work for any reactor. So we are not even going to try to assume anything right now. We are just saying, well, how about I pick a very small space? Let's just start with a tiny little volume in here. So imagine this reactor, maybe it's a 50 cubic meter reactor. So we are saying we're not going to try to estimate everything happening in this 50 cubic meter reactor. Let's make it easy on ourselves. let's just start with 1 cubic millimeter, right? So let's just take a tiny volume in here, 1 cubic millimeter. And then we can say, well, if I know the reaction rate in this 1 cubic millimeter, then I can multiply the volume of that 1 cubic millimeter by the reaction rate in that 1 cubic millimeter. And then I can repeat that exercise across the entire volume. So I can pick all the sub-volumes. So you can imagine a grid. Let's say we split this reactor up into grids, into a grid of 1 cubic millimeter spaces, right? And we add up all the contributions from each of these tiny little reactors that are living inside this overall real reactor. Then we can imagine that in such a small space, the temperature won't change as much, and the concentration across that space, that won't change as much as well. Okay, so we can assume that the smaller the volume, the more constant or the more uniform the reaction is across that space, right? And so that's exactly what we mean when we say, let's add in the reaction rates. Let's add in the reaction in a small space. So we are taking the reaction rate, so reaction rate I, which is a function of volume, and we are going to add up all the volumes. So let's rather write it like this. So this is the reaction rate in the ith sub-volume. And we are going to say times delta V. So V, delta VI. Right, so this is intended to be an argument. It's just telling you which volume you are looking at, right? Think of this as like a volume counter. So you are saying, I'm looking up the reaction rate in this specific volume VI. So we find a specific volume that we are looking at volume VI, and then we multiply by that volume. So the volume of VI, that's delta VI over there. And so if you look at this, the units are now right. It's RI is moles per second per cubic meter, and this is cubic meters, so this is moles per second. This is molar flow rate, moles per second. This is moles per second. This is moles per time, so this is also moles per second. So the units look good here. But we note here that this is across the whole reactor. This is into the whole reactor. This is out from the whole reactor. So it's not enough to look at just one tiny little sub-volume in that reactor. So we need to add up over all these reactors, all these subspaces inside our overall space. And so we can say we want to take the sum over all these volumes. And my apologies, I've been using the wrong notation. Sorry, I need to mute. Okay, someone's watching Game of Thrones in the background. Okay.
In Albania, nodding means no, shaking your head is yes.
Okay, I can't seem to mute, but Kaushik, can you please mute yourself there?
Oh,
yeah. So you two want to join us here?
Okay, I'm gonna have to just.
I'd rather do the ship. I thought that was how we did it.
Okay. All right. So
Well,
yeah.
Yes.
What is this?
So we'll start with protection. This is easy. You go and visit people once a week. You say that we send you an indemnity for production. All right?
Okay. Okay. Just a second. It may have been me. Let's see.
Recording in progress.
Okay. All right. Hopefully our audio is fine now. Okay. So we've got here the overall change, so flow in and flow out, and we are trying to add up all the sub volumes. And this is for component I. And my apologies, this should be the sum over all the volumes. So we are adding up, we should use the subscript J for volume. So we are adding up the rate of formation of component I in sub-volume J. So at the volume position Vj, which has volume delta Vj, this is the contribution to the rate. So that's the contribution from volume J. And then we add up over all volumes J, and then that gives us the total rate of reaction. Any questions or comments on that? Okay, so yeah.
Sorry, can I ask if we can for the reaction rates part, can we write this notation as the integral over volume V times R sub I times dV?
Yeah, that's exactly my next, what I'm going to say next year. So that's right. As you let delta V tend to 0, this becomes more and more accurate, right? So number one, this was always an approximation, right? We said, well, we hope in 1 cubic millimeter, the reaction rate is constant enough, is uniform enough across that space. But strictly speaking, we want to do this in a differential sense. So we take an infinitely small volume, dV like that. And then if you look at this, this should remind you of a Riemann integral. So that's what you're referring to, right, Sanele?
Yes, sir.
Right, so a Riemann integral, remember, it looks something like this, some I. So if you take y some I in delta x sub I, then you can say that if we let delta x tend to 0, so by the way, this was y sub I at x sub I, then this is equal to the integral of y in dx, right? So that's the Riemann integral. So we can rewrite this then as the integral of r sub I in dV. And by the way, when you have an integral in an equation, and you're trying to work out the units in the equation, right? We said moles per second, moles per second, moles per second. Again, the dV part, you just take the units of the V, so this is cubic meters, and then the function itself, moles per cubic meter per second. So this is moles per second overall. Okay, any other questions or comments there? So this equation is completely general. It applies on such an arbitrarily shaped volume. And here we had made no assumptions about the nature of the mixing. We said, in fact, that the concentration would generally vary across the space. We didn't prescribe anything. We didn't say the inlet flow rate has to have this concentration or the outlet flow rate has to have this other concentration. We didn't prescribe anything about this. So this is a really nice general equation. The slight drawback to this in such a general equation is that then you have many different types of variables. And for us to make progress with this and design real reactors, we need to find more specific forms of this, because there are a bunch of variables here, right? You've got the number of moles in the reactor, but then you've got flow rates here, so different types of variables. And then you've got this reaction rate, which is varying generally across the space. So what we want to do now that we've established the general equation, so here's the general equation, Now we seek some specific forms for it. So the first one we'll look at, of course, the Cstr, so continuous stirred tank reactor. And this is a common question that I ask in MCQ type questions. It's does CSTR mean continuously stirred, or is it something else? So it's not continuously stirred, right? It's not about the stirring here. The continuous here refers to the flow. So we have a continuous flow through this type of reactor. So CSTR continuous, there's continuous flow, it's continuously stirred. And well, I guess the tank doesn't tell you much, and we hope it's a reactor. So let's look at what sorts of assumptions we apply there. So we typically draw a CSTR with this type of symbol. It's just that with my mouse, I'm not too good, but so that's your reactor vessel, and then you've got flow in and out of it. And typically, when we draw a stirrer like this, we mean that the contents of that reactor are perfectly mixed. So that's our CSTR. So let's look at modifying our general equation and develop the specific equations for the CSTR. Okay, so we've got continuous flow, first of all. So we know that we have flow in and flow out. So we are going to keep these two terms because there will be some reactors where we don't keep these two terms. The other thing is it's perfectly mixed, right? So if the reactor is perfectly mixed, then that tells us that the concentration is approximately the same everywhere. So even though our flow into the reactor will generally be different to the concentration in the reactor, still, we regard every single point in this reactor as having the exact same concentration. And that will also mean it has the same concentration at the exit. But anyway, we'll talk about that just now. But let's first just let's do it one piece at a time. So first, same concentration and temperature everywhere in the reactor. So what's the simplifying assumption we can make then? Right, so the simplest thing is, if we have the exact same conditions everywhere in this reactor, then that must also mean the reaction rate is the same everywhere. Because as we said just now, the reaction rate depends purely on the concentration and the temperature. So that means the rate is the same everywhere. So the first thing is the rate is independent of the volume. And so this becomes nice and easy. Now, instead of having to worry about these cubic millimeters and adding them all up, we can just take the rate as a constant with respect to volume. And so it's simply RIV. Right, so our equation simplifies to RIV. And then the second thing is that if the concentration and the temperature are the same everywhere in the reactor, that will also include points right next to the exit point from that reactor, right? So once more, the concentration is the same everywhere. And so the concentration at the exit point, the concentration immediately next to the point of exit is also the same as what's in the rest of that reactor. So our exit molar flow rate will, our exit molar flow will have the same concentration CI, which is in the reactor. So to make all that a bit clearer, let's assume a certain reaction first. So say first order. say we are looking at a first order reaction. So minus RA, or rather, let's say first A is going to 2B, for instance, right? Then we are saying that the reaction rate minus RA, the rate of consumption of A, or let's just write it as RA. So component A is not being formed in this reaction, it's being consumed. So it's a minus K times CA, right? And then our reaction looks like this. So this is going to be minus KCA. That's one. And then assume volumetric flow rates in and out as, say, Q in and Q out respectively. So we've got a volumetric exit flow rate here of Q out. And to get a molar flow rate, we need to multiply by the concentration in that flow, in that stream. And we've just said that the concentration in this exit stream must be the same as the concentration just inside the reactor. So that is a CA. Right, so this CA, the concentration in the reactor, is the same as the concentration in the exit stream. And then maybe we also have at the inlet, let the concentration be CA in, right? So yeah, I guess we've switched to component A now. And so the inlet molar flow rate is going to be Q in, and the inlet concentration is C sub A in. Okay, so now we have a much better equation to work with. There is one other thing we can do. The number of moles here, we can rewrite this. Again, the concentration is the same everywhere. So the number of moles can be estimated simply by multiplying the concentration, Ca, by the total volume V. So we can rewrite this as C sub A times V. Okay, now this is a much better equation to work with because you can see there's one variable here, Ca, right? Ca, Ca, Ca. Ca in is different. That's a different number. That's the inlet concentration. Ca is the concentration in the reactor itself, right? So this is much better than this very general form where we don't know how to get each of these individually. All right, so that's a starting point. Any questions there so far? Now, we are generally writing this as if Q in and Q out may be different. So the volumetric flow in may be different to the volumetric flow out. And, you know, if this is a liquid phase reactor, then there's a certain liquid level that we have to keep track of. And so generally, you would want to couple this equation to a separate balance on the total mass in the reactor. So, and assuming the density is the same everywhere, we'll get that dV dt equals Q sub in minus Q sub out. So generally speaking, we would have to solve these equations simultaneously. We'll have to solve for the volume and use the volume in this equation as well. But let's see if we can make a few more assumptions. So if steady volume, then dV dt equals 0, and Q in equals Q out equals, let's just call it Q. Then we can rewrite this equation. Then we don't need this extra balance, and we can just say Well, if dv dt is 0, then v is a constant. So we can pull this constant out here. We don't need to differentiate it in time anymore. This is now simply a q. So this is also q. And that's the equation we have now. Any questions there? And then the next thing we can do is just divide through by v. So dividing by v. Yeah, okay. So dividing by v, we get rid of this here. And then we can take out here q over v. And now we have to group together. Right, we've taken out this q. So now we've got this thing, and we've divided by this v here. Right. So that's what we can say if the volume is steady, right? Now, this thing has a certain special meaning to us. Let's say, let's tau equal v over q, right? And let's think about what that is, right? This is volume, and this is volumetric flow rate, right? So this is cubic meters, and this is cubic meters per second. So if you divide these two, you'll get seconds. So it looks a bit like this has something to do with the time here, right? So this tau, it's related to the time, something about the time about this reactor, and it's about the volume and the flow rate. So this starts to look a bit like the time that the fluid is spending in the reactor. And let's think about something a bit related to that. So if ball is moving at u, so let's say a ball is moving at speed u and passes distance L, then the time the ball spent in space L is, so it's going to be the time the ball spent inside of the distance L divided by U, right? And it's a little bit of a strange thing. It's said, the way I'm saying it here is a little bit strange. We don't think of velocity and time and distance as if something has spent time in that space, but that is what it is, right? If you think about some distance here, and we typically want to know, okay, there's a ball here and we apply a certain velocity u, how long will it take to reach this point, the end point here over this distance L? And so we can say, well, the distance L divided by U, that's going to be the time the ball took to cross the space. And we could say that slightly differently. We could say it's the time the ball spent inside of this interval. And so in a similar way, we can say that the analogy would be that instead of, so here the ball thing is T equals L over U. And the analogy with our fluid flowing through this reactor is that there's a volume V and there's a flow rate Q. And so by analogy with this velocity case, we can think of tau as the average time that the fluid spends in that reactor, right? So V over Q, we can see it has units of time. And if we think about what V and Q mean and this analogy, it looks to us like this is the average amount of time the fluid is spending in that reactor. Any questions on that? right? So this tau looks like the average time we spend in the reactor. And we are going to look at that in more detail later. In fact, there's a whole section where we work with the age, and we'll see we can actually derive and show that this is true. So for now, we would take a little bit of an intuitive approach and say, this seems to us, by analogy with velocity, this seems to us to be the average time the fluid is spending there, right? So this that's our tau. So that's V over Q. Here we actually have Q over V. So the equation that we have here is 1 over tau and all the rest of it. All right, now this equation is looking much friendlier to us. We can see it's all in terms of concentrations. There's a kinetic rate constant here, which we know typically a lab is going to give us. There's some kind of average time spent in the reactor, and it looks like we can measure that quite easily. We can simply look up how big that reactor is, and we can look up the volumetric flow rate. So this tau is an easy number to get. Everything here looks easy. We should know the inlet concentration. So now we seem to have an equation that we can actually work with. We could also say, well, if we are working with the Cstr, where there's a constant flow in and a constant flow out and a constant certain rate of reaction here, that this should be, this is a reactor that can reach steady state. So we are constantly feeding reactants, they're constantly being consumed, and there's something coming out here. So this could reach a steady state. We could reach a certain amount of product here, right? In the example, said A goes to maybe 2B, right? Just as an example. So A comes in, it reacts, it forms some B. So eventually there's a mixture of A and B in here, and then a mixture of A and B leave here. So that can happen all steadily. If the volumetric flow rate is constant, and if these two flows are equal, this could reach a steady state. So if we reach steady state, then we can forget about this term on the left-hand side, leaving us with just the right-hand side here. And so we can say at steady state, or concentration also now, right? Because before we had steady state for volume. Now if we say for concentration also we're at steady state, then we have this. So that's our equation now, and then we could take this across to this side. And then we can say, well, we can surely rewrite this in terms of the conversion. So if you look at this, you could say that this is nothing but Ca in times Xa, right? And that's basically our Cstr. This is the design equation of the Cstr. I actually want to write this a little bit differently. So let's come back to this. Let's leave this as Q over V. And I want to leave this as RA. So instead of, let's go back to the general case, right? So we've got RA, and what we'll do here, let's multiply by V on both sides. So we can say this is RAV, this is Q here, it's Q. And this flow here, right, this is volumetric flow rate times the inlet concentration. So this is the molar flow rate. So FAM. And so our design equation for the Cstr is as simple as this. it's saying to us that if we want to achieve a conversion of X, so let's say we want 80% conversion, and we want to do that at a certain productivity rate, or if this is our molar flow rate, then we just multiply those together, and then we divide by the reaction rate, and then that gives us the volume of the reactor that we need. So this is an incredibly useful equation now. Now it's extremely practical. So from the very general thing that does everything but does nothing at the same time, we now have one simple equation that can be used to get something as practical as the size of the reactor. It's telling us, if you want that conversion at that reaction rate, then that's the volume you must build. Okay. Any questions or comments there? Right, so that's the first equation. So this was all the first case study in the CSTR. So let's look at the next one now. So now let's consider the batch reactor. So the batch reactor, the name tells you that we react things in batches. So we have a reactor again, but what we do here is we load all the reactant into this reactor initially, and then we let it react, and then we open up the reactor and we take out the products. So that's how we operate with a batch reactor. So it basically has no flow, right? In the case of the CSTR, we had flow in and flow out. In the batch reactor case, we have no flow. And so clearly now, these two terms need to go, right? So there's no flow in the batch reactor case. In the batch reactor case, no flow. A little bit bothersome, right? And so now we can just chop out these terms. There's no flow. And the way we've drawn it, you can see we drew a stirrer here. We said this notation typically means there are no concentration or temperature gradients, so the reaction rate is the same everywhere. So this is going to be RIV again. R sub V. Okay, and then again, Ni, we could rewrite as the concentration Ci times the volume V. And then again, if we assume that the volume is not changing here, and I must say in this case, it's much harder for the volume to change, right? Let's think about the couple of cases. If it's a gas phase, then the gas will just occupy the whole volume. So we don't have to worry about the gas case. The volume won't change there. If it's a liquid, then yes, the volume may change slightly. So if you have a reaction rate that changes the number of moles and the molar volume is different between the reactants and products, you might get some slight volume changes, but that's typically not a large amount. So in the batch case, it's volume is approximately constant. So in the batch case, the volumes can cancel. This volume is not really changing with time, so we can regard it as a volume constant out here. And then the volumes can change, can cancel on both sides, leaving us with this equation. And then again, it would be nice to rewrite this in terms of conversions, conversions and initial amounts and all that. So, so let's see, how would we write this as initial amounts? So we would have a certain initial number of moles in the reactor, N A naught. Let's say we are doing all this as component A, right? So Na naught, and then we would say the current number of moles Na equals Na naught times 1 minus X. So the amount left over after X Na naught has reacted is Na. So that's there. And so our concentration Ca equals Ca naught, which is going to be Na naught divided by V times 1 minus X, XA, if you like, XA. Right, so that's our concentration. And Na and V are constant. Then one derivative of 1 is 0, and then you've got a minus here. So we can rewrite this side as minus Na naught over V A. So it looks like that. Okay, so that's the batch reactor. And if we compare here, let's see, I'm just trying to get them on the same page. So let's multiply this V out here. So this Na naught and Na naught times V here. So that's the batch reactor. So if you look at this and you look here, you can see there are some similarity, this one here, there are some similarities, right? Your Cstr, so you've got Fa in X, here you've got Na naught ddt of X, and there's an RAV here. Okay, we'll come back to how to view those as similar, right? But the right-hand side at least is the same RAV, right? Okay, now let's look at the last type, the plug flow reactor. Maybe just before that, any questions or comments there? Okay, so now let's look at so-called plug flow reactor. So in plug flow, you have, let's imagine a cylindrical tube. So you've got your reactor here as a long cylindrical tube, and you're feeding and you are withdrawing. So you've got flow like that. And in plug flow, we regard the fluid as flowing in little plugs through the reactor. So yes, we know we have a continuous stream. For example, if this is a liquid phase reaction, you've got a continuous stream of liquid here. But if you think about the liquid that's flowing in, you could think of it as little plugs of fluid, right? You can discretize this fluid and say, well, this liquid, I can break it down into little boxes of liquid. And so when each of these little boxes enter the reactor, in the case of plug flow, they occupy a plug space like this. In other words, they occupy some axial distance, and I'm drawing them, I should draw them thinner than that because of the way I drew those boxes there. So it enters, and each one becomes its own little plug that's moving through the reactor. And by plug, we do mean a couple of specific things. So we mean that So we mean that in this plug, everything is perfectly mixed radially. So you've got the same concentration across this plug in terms of the radial direction. But in terms of the axial direction, the concentration will differ. So if you were to look at the concentration across the different plugs, you may see something like this. So for example, you are feeding pure A into this reactor. So you are feeding it at a high concentration here. And as these little plugs chug their way down there, they keep reacting. Remember, A is going to 2B in our example. So A is converted to 2B. So if we were to look at a plug a little distance down from the entry point, then a certain amount has reacted to give us B. And as we go further, more and more get reacted. And so A slowly vanishes as we look down this tube. So we have an axial variation. Our concentration changes in the Z direction, but it's not changing in the R direction, right? We can imagine a center line for this tube. So if we look across the center line, we are saying that in this direction, there's no change, right? If we look at any one plug, there's no change in this concentration in this one plug. So the reaction rate is the same at all points in this one plug. But the moment you look in the Z direction, there is going to be a difference. The concentration in this plug is different to the concentration in this plug. And so the reaction rates are different. So with that being the case, we need to develop a balance over, and again, this space is a little bit complicated now. So let's take a small volume. Let's choose some position down the tube. Let's say position Z here, and at position Z plus delta Z. And the delta Z is going to be small, right? We are talking about, again, like a millimeter. So maybe this is a 5-meter tube, and we are looking 1 meter into the reactor, and then we are looking 1 millimeter next to that. So, so this point is 1 meter, and this point is 1 meter plus 1 millimeter. So we are looking at a specific thin little plug over here. So let's see what we can say about that. Okay, let's just copy this thing ourselves. Yeah, this snipping tool. Right, so let's take this plug and write a nice little balance on it. So we are now talking about plug flow reactors. Plug flow reactors. So now let's think about this space here. We want the rate of change of the moles in that space. So we can say ddt of the moles of A, and these are the moles of A. That doesn't. So these are the moles of A between position Z and Z plus delta Z, right? So we are starting out with a very tiny little thing, a little sliver here. What's the rate of change of moles in this tiny little space? So first off, we can see that there is flow across this this space, right? So we've got the fluid is flowing through this tube. So some of the fluid is going to just flow in here, and then some will just flow out there. So we can say there's a molar flow rate, and now our molar flow rate, in contrast to earlier, where we just said there's 1 molar flow in and 1 flow out of the whole reactor. Now we are defining molar flow rates inside of the reactor. So we can say it's a kind of internal molar flow rate of component A. And so we have to specify at what position. So the molar flow coming in at position Z, that will enter this plug, the plug that's over this space here. So that's what's coming in. And then leaving the space will be the same flow, and this will be at position Z plus delta Z, right? So that's flow into and out of the space. And then we've got the reaction that's also happening in here. And we said that the concentration is the same everywhere in this plug. We said, yeah, and we also assume that the temperature is the same everywhere in this plug. So we can say then that this is RA, but we should specify this is RA at position Z, right? Because the rates do change, right? We know the concentration changes across the space in the Z direction. So we need to specify which Z among RA. So that's RA. And then we need to multiply by the volume of the space. Now, it's between Z and Z plus delta Z. So the thickness of the space is delta Z. And then we need to multiply by the area also. So the cross-sectional area, which we can just call AC. So this pipeline will have a certain cross-sectional area. So that's the volume of the space of interest. There is a little approximation that we are making here also. We are taking the reaction rate in the sliver as being the rate at the left edge, right? When we say RA at Z, that's the left edge of the sliver. Whereas we should really be averaging between RA at Z and RA at Z plus delta Z. But of course, what we are doing here is we'll take that as the approximate rate, and then we'll let delta Z go to 0, and then it becomes exact, right? Any questions or comments so far? Okay, so that's the starting point of our balance. And then the next thing to do is express this number of moles using this volume here. So in a similar way, we can say that this can be rewritten as the concentration at position Z times the volume there. So we want the number of moles in this little sliver. So we multiply it by the concentration times the volume of that sliver. So let's do that. So we rewrite this as, and I'm just going to copy this volume here. So this is going to be CA of Z times that. Ooh. So that's what we have there. And now, of course, we can say AC and delta Z, those are not functions of time. Those are chosen fixed points in space. So we can just divide both sides by that. And so, another thing we should do is instead of writing this as molar flow rates, we can say this is the same as the concentration of A at position Z multiplied by the volumetric flow rate at that position Z. And again, let's assume the volumetric flow rate is the same across this whole space. So that's there. And then here also we can say this is the concentration at Z plus delta Z times the volumetric flow rate there. Now, one other thing we can do is say, well, this volumetric flow rate, we've defined the cross-sectional area here. So the volumetric flow rate must be the cross-sectional area times the linear velocity. So we can re-express this Q as AC times U. And we're going to do the same here, Q is AC times U. So that's nice because now all these ACs can cancel. And let's see, a U, there's a constant U between these two terms. And this delta Z. So we want to divide everywhere by AC delta Z. So doing that, dividing by AC delta Z. This AC can vanish, and this AC can vanish, and we can group these two. So we can take this U out here. U times this stuff, and divide by, yeah, so here we need to divide by delta Z, right? And then here we simply divide AC delta Z. Okay. And now we can see we can do the obvious thing, which is recognize this as a derivative if we let delta Z tend to 0. So we can rewrite this as minus, okay, let's put the minus there and call this DCA DZ. Okay. So just compare these two here. You agree that this is the same as minus dc dz, right? Normally we go z plus delta z minus the thing at z. So here the positions are reversed. So we have to say minus here, but the rest is simply dc dz. Okay. Any questions or comments there? Right. So again, this is the unsteady state version of the so-called plug flow reactor. And again, this could reach a steady state, right? And by the way, it's not automatic. Not everything reaches steady state. Like think about the batch reactor. This batch reactor, you are loading things in, let it all react, and then you get something at the end. So there's no steady state happening there. Well, there's the trivial steady state if everything runs out and it's just staying there. So, but that's a trivial steady state. It's not doing any reaction for us at that time. So, but here you can steadily be reacting something. You can steadily be producing a product. So you can reach a good steady state here. You are constantly feeding A in. A is constantly reacting across the space and A is coming out. Excuse me. So you can reach steady state in this plug flow reactor. So we can say here, at steady state, we get, and then your equation looks like this. So the left-hand side becomes a 0, and I'm taking this across. So that's what we have now. And by the way, you've got here dz and u. Remember what we said earlier about the velocity and the distance something is crossing. So if we look at this, we can read this as dc d tau. Yeah, so in this, it's in effect the same tau as before. It's the same space time. It's the same volume divided by flow rate. Maybe let's prove that. So we can say here, tau equals V over Q, and V is nothing but AC times, let's call it delta Z. So this, by this delta Z, I mean the whole tube, right? Delta Z being the whole tube. So that's the volume of the tube. And then the volumetric flow rate through the tube is going to be the velocity times the area, AC. And so the ACs can cancel, leaving us with delta Z over U. So you can see your space-time does relate to distance and velocity like this. And you can check the units. That's meters per second. So meters over meters per second is seconds. So that's like a time-like variable again. Okay, so we have this form of equation. So let's put them all together now. So this is a PFR at steady state. Then we've got a CSTR, which we wrote like that. I wonder, let's just copy both versions. Maybe one would work better with what we have here. So CSTR steady state. Sorry, my editing is really bad today. Okay. And then your batch reactor. Batch reactor looks like that. So let's reduce them all to a volume basis. So let's see, how do we do that? Let's if we put in an A up there and an A down here. I always waste time on PFR doing this kind of thing. So this is a Q. This is like a dV. So yeah, I guess that kind of works. Especially if we rewrite this in terms of X. So you could say this is like for the PFR CA in, and this is XA. Right, then if you look here and you look here, you can see how similar these two equations look. You've got an RA out here, you've got a Q and a V in those positions. In this case, it's a dV. You've got a CA in and an X here, like that. Right, and similarly, we could do this here. So if we divide this by V, then of course, this is nothing but CA naught. Right, so there's no Q in this case, but you've got a T here. So and in fact, then so we know this is 1 over tau here, and this Q over dV. So we can think of this as a d tau. So if you look at these three equations, they look remarkably the same, right? So you've got a 1 over time, right? 1 over time, CA in, and in a batch, there's no inlet flow, but there's an initial amount. You've got an X sitting there, and you've got a rate sitting there. So these are all different, these are totally different situations, right? This is perfectly mixed flow reactor. And yeah, flow. This is no flow. And this one is no mix, right? PFR, it's mixed radially, but not axially. And in fact, the way I think of these two reactors is on opposite extremes of the spectrum. I think of the Cstr as perfectly mixed, and I think of the plug flow as perfectly not mixed, right? Plug flow, everything stays in plugs, right? It's the ultimate view of segregation. Everything comes in, stays together, and leaves together. So that's completely segregated, whereas Cstr is completely mixed. Batch is completely mixed, but it's completely no flow. These are completely flow. So in a way, these three are kind of different combinations of two different things, right? One, the nature of the mixing, two, the nature of the flow. And yet they all seem to have a kind of close analogy among them. And we'll see what that means as we go. Another thing to think about is the Cstr is actually the worst possible reactor out of all these. Why do I say that? Can someone help us? Why could we say the Cstr is the absolute worst type of reactor? Any takers? Sandile? Oh, you muted again. Okay. Please go ahead. Nkazumulo, am I saying your name right?
Yes, sir. Is it because we have to control the inlet and flow and the inlet flow rate and the outlet flow rate?
So that's true. We do have
of the
to
control
control
system.
those. To get good performance, we're going to have to control those flows. So that's one thing. Please continue. So yeah.
That's all I was going to say.
Okay, so yeah, that's right. We do have to control these, and these reactors are quite sensitive, and there's quite a lot of effort to get this to operate properly. So there's a lot of control we have to work on in this case. But the other thing to think about is, well, number one, I didn't even say what the criterion is. Whenever someone says, well, you are the worst, then you must ask them, well, according to what? You don't like how tall I am or short I am, or, you know, what is it? So the criterion here is the reaction rate. So in everything in this course, we'll always come back to the reaction rate. Can I get a nice reaction rate? And the reaction rate here in the CSTR is actually the lowest among the three. And the reason is because of this perfect mixing, it means that steadily, right? That means for all time, you are stuck to this one low concentration in this whole reactor. That means there's no position in this reactor where you have a nice high reaction rate. So let's say we do get a nice high conversion, right? We think of that as a good thing, right? Generally speaking, we would say, oh, we got 80% conversion. That's a good thing. But if we are using a CSTR, if you've got 80% conversion, let's say we were feeding 100 moles per cubic meter in, and we got 80% conversion, then that means our concentration of A is 20 moles per cubic meter in this reactor. That means every single point in this reactor has 20 moles per cubic meter. So our reaction rate is stuck to that one low value through the whole volume of this reactor. Let's think by contrast with the plug flow case. We are feeding again at 100 moles per cubic meter in, and we get 80%, right? But that 80% is at the end point here. When we say, well, I got 80% out of my PFR, that's talking about coming out here, I've got an 80%. If I look at what's coming out here, it's been 80% conversion. That means right here, it's 80%. But up here, there's no conversion as yet. So up here, you've still got a high concentration, approximately 100 moles per cubic meter here. So you've got lots of volume where you've got a much higher concentration of A and hence a high reaction rate. So this reactor overall is going to be smaller than the CSTR. This CSTR, to maintain that 80%, maybe it's going to take you 100 cubic meters. And it might be that with only 20 cubic meters, you get your 80% here. And that's because you've got some high rate regions. So the plug flow reactor makes good use of its volume. In terms of the batch reactor, how about that one? So in the batch reactor case, well, I guess I deleted it by now. But in the batch reactor case, yes, it's perfectly mixed everywhere, but it doesn't instantaneously reach 80%. When we are reacting in the batch reactor, we are talking about over time. So maybe there's 1 hour of operation. So after 1 hour of operation, right, we started with 0 conversion, and then it slowly gets to 80%, and we say, okay, I'm stopping there. That's my 80%. So at the end of the cycle, we reach 80% in this batch reactor. But there's a nice space of time where the conversion was still low, right? In fact, for most of the life here, the conversion is much lower than 80%. And so we have a high reaction rate for a good period of time. So in the batch case, we are making better use of the time in this reactor. In the PFR, we are making better use of the space in this tube. So the CSTR can't do anything in both space and time, right? It's running at steady state and is perfectly mixed everywhere. So it is stuck to one low rate, and that's why the CSTRs are the biggest reactors out of the three. And by the way, we are talking as if there are 3 reactors here. There are actually only 2. There's this reactor, and these 2 reactors are the same, right? I'm not going to explain exactly why right now, I want you to think about that. Why is the batch reactor equal to the Cstr? Okay. So we'll talk about that another time. But the Cstr is the worst user of its volume. It can reach 80%, but it's going to require a bigger volume. Now, the other side of it is, this is the easiest one to do, right? The Cstr is the easiest one to construct. All we need is a big container, and we need to stick a stirrer in, and that's a Cstr. Well, you need to drive a flow through it, but that's all, right? This is practically feasible. This is how cooking is done, for example. Well, not really with the flow, but anyway. But you've got a container and you stir the container. That's all it is. So intensely practical, but terrible performance, right? This PFR, this looks great here, right? You get a nice high rate, but do things stay in such segregated ways? Does anything stay to itself? It keeps to itself all the way and then exits? No, there's going to be dispersion, right? As these plugs flow through here, some will diffuse ahead, some due to friction on the walls will get mixed, and so there'll be some lateral movement as well. So this is practically hard to accomplish. It's very hard to get pure plug flow. There are some attempts with micro channel reactors and things like that, where you really do have tiny, thin, long little tubes, and that gets you closer to that. But even then, you don't really get it. There's always going to be some velocity profile. And so this is practically undoable. In the batch case, you can force it to be closed off and there's no flow. But again, you are relying on perfect mixing here. Well, that's not really, it's not really a feature. You can, yeah, you can accomplish good mixing, and there's no flow, so you can accomplish this. And that's why batch reactors persist to this day. You might think, well, the moment we thought of CSTRs, where you can flow things through and constantly get product out, we should have immediately axed all batch reactors. But the reality is we still have batch reactors today, partly because of the reason I mentioned over there, that this is a bad use of its volume, partly because in the fine chemicals industry, you can do a lot of good control over such a restrained space. So you can control these reactors really nicely. So as your classmate said just now, yeah, it's quite taxing to control these flow reactors because of flow in and flow out. So in fine chemicals like pharmaceuticals, they do use batch reactors and they can control things over time and all of that. So those are some of the practical things we'll be looking at. Yeah, so that's those are the 3 ideal types of reactor. And yeah, I've spent so much time talking, we didn't get much of a look at the tutorial, but I'm hoping you'll say that, well, all of that then sets you up nicely to answer these problems. So of course you've got the resource here where you've got the problems worked out for you. So quite a lot of this has relevance. And then in this tutorial, use that theory and follow that method, and you'll be able to work through this as well. Any questions or comments so far? Any takers on me saying that these 2 reactors are equal? The PFR and the batch reactor, why are they the same? Looks like you need to sleep on that one. Okay. All right, I guess that's it for today, unless anyone has any last questions or comments. Okay, seems not. Then Thank you and see you next time.